host today. So my name is Alois Mbutura, and I lead hardware at Coyote. My specialization is in hardware design, wireless planning, and communications. I have a background in electrical engineering, specializing in communication systems and telecoms, radio frequency planning, and basically communications of devices and also embedded systems. I'll hand it over to my presenter.
So, hi guys, I'm Adam Zakode. I work with Alois at Coyote. I am the lead for the software department. I have a specialization in system architecture planning, payments, and system integration. I have a background also in telecommunication and information engineering. That was my major and minor, respectively, in college. I mostly delve into software architecture design within the IoT space, and I look forward to sharing a bit of knowledge on that within this session. Over to you, Alois.
Thank you, Adams. So also a little bit about where we work at Coyote. So we like to describe Coyote as a sensor and data management firm. It wasn't formed too long ago in 2017, and the main purpose is to give sensor measurement, data management, and visualization solutions towards clients. And we also offer consultancy, especially when it comes to communication systems, to other IT firms. And also we do focus across the board with companies, nonprofit organizations, among other sort of clients. So in terms of what we focus on in terms of our technology stack is that we focus on people deploying scientific measurement solutions, pay-go or pay-G as they call it, metering, GPS tracking, amongst other solutions out there within the field. Our main aim is actually to have a software architecture that people can take up within sort of their firms, and we soften the process towards companies willing to shift towards new and emerging technologies. Great. So we'll start a little bit with regards to my section, Hydra Perspectives. I have had across the room that there are quite a number of people from power, airline, telecoms, the energy field, oil, locomotive. And what I'll do today is that I'll give a bit of hardware perspectives into understanding the Internet of Things. So this comes from my personal experience, and I hope that it will be useful for you. As an outline to my presentation, so we will delve with various aspects, which includes sensor types, connectivity options, how do I connect my sensors to the cloud, how to plan an IoT deployment, and finally, this sort of new term that's coming up called fog computing, and also redundancy, and how to handle it in wireless networks. If you're dealing with mostly data, you'll notice that this bit will mostly be handled by somebody else, but if there is nobody else to handle it, you may most likely be the one to handle it because it does affect the quality of data that you receive, and thus it's good to plan out your deployment well in order for you to receive correct data. Just getting into the sensors that we have. So this is a broad spectrum of sensors that are applicable. I will outline a few or pick a few based on what I have gotten out so far. And just by definition, this whole term of which we meet called IoT. Therefore, IoT is, I like to define it as an aggregation of data from physical sensors and its communications to other machines. So this is sort of an automated process, meaning from device to cloud or device to device in the case where you have peer-to-peer networks and not a common server client architecture. As to the sensors that are there, this includes, for example, in the automotive industry, you might find several machine vision or optical sensors. So this is usually useful when implementing computer vision, of which one sees it especially with self-driving cars and also traffic systems. We also have other sensors, which also includes chemical or gas sensors. So this is usually useful when you're talking about OSHA or occupational safety and health, whereby you need to monitor the sort of gases that are being emitted from an industrial place, whether it's in mining, whether it's in industry, or whatever industry that, that one is partaking in. There are also other sensors from the whole suite. Depending upon what you want, do you want proximity? So it depends upon what's the need. Do you want to send somebody who's close proximity? Are you measuring speed? What sort of, do you want to measure temperature, humidity? There are a whole suite of sensors that are applicable, and this just explains a brief of what is possible in terms of measurement. So just to get a bit of feel from the class is, I'd like to know from a few, probably Shiv can pick a few people just to state what sensors are mostly applicable from this list within the industry. That would help guiding going forward.
Any volunteers?
From an airplane point of view, one could say that the airplane is a sensor that happens to carry people. We have possible systems that record everything from fuel pumps to fuel flow to fuel pressure, fuel temperature, outside ambient sensors, wind speed, apparent ground speed, engine, like it is basically a sensor made up of sensors that happen to carry people. So yeah.
Okay, great.
Again, yeah.
Yes,
but,
please go ahead.
Yeah, so yeah, that's true, because if you think about the issues with the Boeing MAX series and the sensor defect that caused the airline to ground all those planes, right? So sensors are very important in airlines business. So how about you guys, people working in tobacco? Do you, right? Anybody else?
I'd say, oh, and this is the locomotive industry, by the way, because we have different sets of components and machines, and there's different sensors in those. So some of them you'd actually have maybe temperature gradients, so you know that's working properly or as designed. You'd have pressure measured, you know, from one filter to another. So it's also a range of these sensors between flow, pressure, speed, depending on the component.
Yeah, thank you very much, Lungi.
Okay. Probably one more.
Yeah, last call for volunteers. Jacqueline? Toby?
Yeah. So in the power sector, we the gas turbine has a couple of sensors all around it. You know, reading the operation data, the ones that the control engineers or the operators actually look at when they are actually operating the gas turbine, start up to full load, to even when they are dispatching the load at even part load of the gas turbine. And then we also have protection sensors that reading certain limits on the gas turbine or on certain parts of the gas turbine. So when there are actually issues with the units, and then we also have the ones that are used for predicting failures as well. That goes to the center that's been, all the data has been monitored. So we have sensors from the compressor down to the fuel area, and then even to the exhaust, measuring a lot of data, and analysts use that data to know when
the issues.
Can you hear me?
Okay.
Yes, we can hear you very well. Yeah.
Great. Yeah. Yes. Yeah. Great. Okay. Thank you. Thank you for all your contributions. Cool. Moving on. as much as you have sensors, you do need a way to connect them to the cloud or to other machines within the vicinity. If you're connecting a machine to machine without the cloud or the internet being as an intermediary, we usually call that a peer-to-peer network, and the server that sort of like mediates between all the devices. For example, if you have 2,000 devices at a plant, and thus all the devices communicate, for example, to a local server or an on-premises server or cloud server. So therefore, that sort of IoT model follows a server-client architecture, whereby the devices are very small, very low power, and then the server, because it's on the cloud, it's able to draw as much power as it can in order to do all this processing from all this data. And in order to connect all these devices to the cloud or peer-to-peer, there are various technologies that have come up along the years. So the following represents quite a few of this. So you have, within the cellular networks, you have protocols such as, for example, LTE. You have 3G, 2G. So all these come within sort of like within the cellular era, which is beyond 2003, and it keeps on progressing. Within the cellular networks, you have essentially what you call releases from the Global Standardization Committee that sort of like states how the protocol should be progressed. So it goes release after release after release. You'd have release 15, 16, 17, and progressing. You also have various protocols, for example, that also work on a much smaller scale. For example, Wi-Fi, which nobody has to pay for, and also works on the free spectrum, the free frequency spectrum. Also, Bluetooth works together with Wi-Fi. And you also have various other protocols that come up in order to support machine-to-machine communication, and that are very low power. For example, RFID. So when one is looking at the exact protocol to use, you need to know, for example, things like what is the range that I'm looking at? Is there any sort of like security that needs to be implemented within, for example, the protocols? Is it secure enough? What are the regulations, the context by which I am operating? Is it within the banking industry? Usually, for example, here in Kenya, is that you have the banking industry stipulating that if you are a data processor, you have to process that data locally within the country. And they do have to do physical inspection of your space to ensure that the servers, that no data moves outside the country. Therefore, you need to look at, does my communication means allow that? Is it an open communication means, one that is freely implemented, or is it one that I have to obtain a license for? So all this affect the connectivity options that one chooses. Therefore, you just need to be aware of it and also keep cognizant of the connectivity options that are available. Do your research, that will go a long way. So we go through a sample application. For example, this is a factory space. So you're having assets along a factory line. You have 2 production lines and the whole factory space, and you would like to monitor assets within an indoor space. So I will explain the problem with this application that you find. Within the real world, you find that people do localization tracking, but majority of the tracking that usually happens outdoor. But what happens when you don't have access to satellites from outdoor? How does one know where a specific asset is within, for example, like the factory floor? So within the protocols that I previously mentioned, there was an interesting protocol that came up approximately 1 to 2 years ago. Well, I'm not too sure of the timeline, but that's an approximation. So what happened is that it allows sort of like the asset to send a message, a wireless message. So this wireless message is riding on a protocol, ZigBee. So ZigBee is a common protocol that is used especially in like home automation, industrial automation, and it allows sort of like the asset to communicate to certain receivers placed at strategic positions on the factory floor. And this allows monitoring of the indoor asset till a resolution of around 10 to plus or minus 10 centimeters within 2D or 3D space in order for accurate localization of the asset that you're looking for. So that means that you can get really fine details with regards to where a specific asset is on the factory floor. And also that also includes if you're wanting to track people and also inanimate assets. So in order to build, for example, a system like that, so you have two essential assets. Going back to this, on the left, you see that there's sort of like this reference tag. The reference tag is worn by the asset or is placed on the asset, and you have receivers placed at strategic locations on the factory floor. The tag sends a message, and then all receivers receive it. So it works the same way nearly how satellite does work, whereby one message received by several receivers. In satellite, it's the opposite. Various satellites send messages that are received by, for example, the tracker, but this happens in the opposite way. One message sent, received by the receiver, and the receiver uses, for example, calculates like the time that the message trigonometry in order to calculate its position. And this also can be tied to the internet on this end. So in order to have proper communication, you need to know where is the receiver and where is the transmitter. And also, usually you'd find the communication either happening using a wire, for example, if it's LAN, or it could be wireless. If it is wireless, you need to know, for example, how well is my device radiating best? So this is something that's usually overlooked. When you buy a device anywhere, one usually needs to know this, especially when you're talking about if you're deploying, for example, on a factory floor. You'd mostly have the receivers in this use case. You'd have the receivers on top where there is as minimal obstruction as possible so that a receiver is able to have as wide of a view of the factory floor. Therefore, right here on the left, you have, these are test centers that you have that occur for devices. So you take your device that you've designed to a chamber, otherwise called an anechoic chamber. You have these rigid elements on the walls. So what this do is that it's a testing area. So what it does is that it tests as to how well your device is communicating, what power is it sending, and also it gives you a plot of how best your device is radiating its energy, of which the communication is sent by. So you can have an omnidirectional pattern whereby the energy is sent nearly equally in all directions. This is really good when you're talking about, for example, GPS receivers and various other devices that need to communicate in all directions. You can also have it in a directional manner. Directional manner is followed, especially when you're talking about in the aircraft industry. You have, for example, sometimes transponders that do communicate to the ground stations. You also have within the telecoms industry, you have directional antennas, 3 of them, each covering 120 degrees in order to cover a full 360. So what this allows is that it pushes the energy out further in one direction as opposed to what you'd get with essentially one antenna. So you have 3 antennas all pushing out energy as far as possible in order to get the maximum range possible. And that is why you're able to receive cellular, for example, in as low, as deep, if you're in basement, you can still receive a cellular reception quite well. So the question comes about, how do I handle harsh environments if I'm in a factory floor? On the left, you have what essentially is like a Wi-Fi antenna. In physical space, this is how the antenna, in fact, does radiate, in that the walls do offer some obstruction towards the signal itself. So one usually needs to measure this when it's out in the field. So for example, we at Coyote, we have done deployments also over wide areas, whereby you'd have one antenna beaming out energy over a radius of around 10 kilometers, 15 kilometers. And thus, there are 2 variables by which we look at to see how well the energy is spread out. The first one is whereby we check the signal strength. That tells us how well is the signal, how high of a signal do we receive? And there is a second one called signal to noise ratio, or that defines the signal quality. How much noise am I receiving as opposed to the signal itself? on a TV, this usually ends up showing up as static. For example, if you have a DSTV antenna or any DVB antenna or any DVB receiver that receives digital broadcast, this usually shows up sometimes also as flickering within the channel. So one usually needs to measure this over a couple of days in order to ensure that you do receive the correct data, and also that your signal is spread out in order to accommodate all transmitters and all receivers. Going quickly into this new concept called fog computing. I only touch on fog computing because I believe that it's one of the key pillars, especially when you're talking about within the industrial space. The industrial space is a bit different from the general mass market devices because an industry is essentially rated by the amount of uptime it has. Therefore, the devices by which that run the industry need to have very good uptime and also need to be very resilient, for example, to network outages, to handle power. That's why you'll see that there'll be power, local power within the industrial space itself in order to keep that uptime. We did a deployment some time back when I was talking about the 10-kilometer radius that we covered. We did notice that, so we are using a protocol called LoRa. So LoRa is a protocol made by a French company, a French semiconductor company called Semtech. And they do offer sort of like what we call gateways. So gateways are implemented by network implementers. So for example, Coyote has its own gateway that it manufactures. And we implement the LoRaWAN protocol, the LoRaWAN specification. So you have devices, edge devices. This includes water meters, temperature sensors, also within the industrial space, that do communicate to devices or gateways. The gateways take the data from the devices and forward it to the cloud or data center. But then there is a complication that we met while deploying this. On paper, it looks like a brilliant protocol to use. But we did notice that while implementing this in Africa, if you're using, for example, a cellular backhaul that you see right here between the gateway and the cloud, the latency would be so much that that the downlink message, for example, if you're sending data up and you're expecting to receive data back. So what the LoRaWAN specification states is that you send data, an uplink message that you see here on the right. The data is sent to the gateway, and after around 1 second, so the device waits for 1 second on the spot and waits for a downlink message. But the problem was that between the gateway and the cloud, it would add, according to our measurements, added around 800 to 1.6 seconds of latency. So every time we would test, we would always miss this slot. That means that there would be no downlink that would happen. LoRa has been implemented in Europe. So you find that they usually use either fiber to implement this, but not cellular. But in Africa, cellular is like one of the most widespread protocols that you have. But we kept on seeing the same problem, for example, with 4G. We kept on seeing the same problem with 3G, with 2G. And therefore, this formed a problem of which we had to solve. So how do we solve it? So I'd like to get a few ideas from the class as to how one would solve this, whereby you have devices communicating here to a gateway, but the latency here is too much on the backhaul connection. How would one essentially accommodate this? Shiv, any idea of somebody who can probably answer this?
Chief, I think you're on mute. We can't hear you.
Oh, sorry about that. I have some experience using LoRa. I was using LoRa for air quality measurement. So we had like monitoring station that we placed around a university, and again, like you were saying, this we were interested in LoRa because of the large large area. But this didn't really work really well because we were having the same latency issue that you were talking about. Because we wanted to place the air quality sensors in cars, so moving vehicles in the area around the university, and have a mobile. Actually, our final objective was to have sensors on drones and have the drone fly around and capture air quality data. And we had the same issues because we're using cellular for uploading and for the downlink, so it didn't really work. So I think we have some people from telco who can give us some ideas. Adenka? Adenka? Anybody working in telco industry?
Hi, I'm in the telco industry, yes, but more on the enterprise side. So the network side is a bit out of my depth.
Okay. Okay, so well, basically one way that we did work around this is we had like local gateways, and so we got points where we were using. It was going to be connecting to the fiber optic cables, and that's how like we managed to get it. But our network was only as big as where we could put gateways on those fiber optic cables. So we got people who were living in the vicinity of the university to donate their internet time. So we just went and put like gateways at their place. But it wasn't the ideal solution we were looking for. Yeah. So what was your approach?
Thank you.
May I suggest something or ask something?
Yes, Andrew.
Yes. So in terms of
sorry.
Sure, please go ahead.
Yeah, Andrew.
We faced a similar issue when we were working with handhelds about 10, 11 years ago, except that it wasn't a latency issue. Sometimes the connection would just drop completely. So what we did was we had a copy of the local data on the device locally, and then we either kept up a buffer, and then we sent when we had signal and received when we had signal. But in your case, it looks similar. So I don't know if you do have a some type of buffer. In your case, not the edge devices, but on the actual fog nodes or your gateways. So when a receive slot does come up on the edge devices to receive it, you can sort of just push stuff in that specific time slot. So if you don't have a buffer on your edge devices to receive, you can at least have a buffer on your fog nodes. Given the sensor indicators that you have there, I would totally guess that the buffer size wouldn't really be very big, maybe a couple of megabytes. Was that the situation that you were facing, where it wasn't a large amount of data that you needed to send back to the edge devices? It was just you couldn't.
Yes, that was the case, whereby we just couldn't send the data. Typical data widths of what we were sending to the devices was anywhere between 18 bytes to around 60 bytes. Therefore, what we did is that we allow the devices, so we don't affect any of the devices. So what we do is that we modified the fog nodes and had a local copy of whatever was running on the server, the critical components that was running on the server, running right on the fog nodes. So that meant that anytime there would be any disconnection or any downtime on the backhaul, the fog nodes would take over. And if you do your calculations and you calculate that each message is around 60 bytes, and you have approximately 256 megabytes of RAM on the device. So you can store that data for quite a long time and just push it back out when the backhaul comes up.
Okay.
Yeah, so that's how we solved it in our case.
So basically, it's just a message
Thanks.
queue system or a message bus.
Yes. Yes. So it also incorporates part of the downlink aspects of from the server and implements it directly on the fog nodes itself. So it receives that data, and then sort of like the uplink and downlink are asynchronous. That means that you're able to get the downlink data. So if you want to send, for example, switch off a certain device, you'd send it out, and then it's not dependent in any way on the reading that is received. So you're able to push that directly onto the fog nodes, allowing that when the device sends data, within this 1 second, window, you're able to send this data back down as fast as possible to the edge devices directly from the fog nodes.
Okay.
I trust it's clear?
Yes.
Okay. On to the final concept of today, of which we're talking about understanding redundancy in the industrial space, is that, as I mentioned, redundancy helps when you essentially have an network outage, especially when you're having this sort of topology whereby you have a backhaul and then the backhaul is not available. So I define redundancy as the ability to perform message caching locally on the gateway. That means that if you're having uplinks, the message would be cached directly on the gateway itself before being pushed out when it's available. For example, some of the storage sizes that one has is that you might have on industrial gateways that do run, that I usually see, you might have 512 megabytes of hard disk space, or others called flash space. You also have some database type that is also storing this data. And for example, one of these fog nodes right here, for example, in the case for LoRaWAN, is that it can accommodate theoretically up to around 2,000 devices. So if you have these devices sending out at random times, you need to make sure that in terms of how fast you write to the database, your database is able to keep up with the maximum throughput that is received directly on the fog nodes. With this statement of redundancy, it's not a necessity that there are downlinks handled, but just that the main critical components of a network are handled as close to the edge devices as possible. And this also depends upon like what situation are you looking at? Is it a life or death situation? Is it medical? Whereby you need to make sure that the message is received. And it's not just a matter of, if there's network, I'll send it. If it's received, I do not know, but I'll just send the data anyway. So this is really defined as quality of service. There are various levels of quality of service. And how you look at it is that the better a network is, for example, LAN. LAN is always better than Wi-Fi. The reason being is that LAN is mostly available. It uses a wired network. It's available when you need it. And also, this is also on the hardware level. On the protocol level, there are also industrial protocols that are built in order to support a better quality of service. For example, at the factory space, at the workspace, wherever the area of implementation is. So thank you. I've reached the end of my slides. If there's anybody who probably has a question that needs to ask, we have 3 minutes. 3 minutes question time.
Question time. Okay, so when you have all these sensors deployed, like in one of the examples you were showing where you were using something like ZigBee to identify where some asset is on the factory floor, do you have to recalibrate? Because I guess with time, the sensors might slowly degrade in performance. So do you have to recalibrate, and if so, like how often, or how do you detect that, you know, oh, we have to go back there and recalibrate the sensor so that we can know, based on strength of sensor, the distance that asset is from that receiver?
Yes. So with regards to what usually changes directly on the device is that so far we've not met that case yet, but in terms of what usually varies on the device is you usually have aging. So aging is a factor that happens on all devices. It's a statistical factor whereby, for example, if I was sending at a certain frequency, the frequency would sort of like deviate over time. And also, so majority of these are very, in terms of the presentation that I have done, which is on this slide, you'd have, for example, this tag right here. So majority of the calculation happens directly on this line, but the factor that we have seen that mostly affects these devices is the time. So all these receivers need to be synchronized at the same time in order for it to calculate the time extremely well. Therefore, what we do is that we usually have a wired connection connecting all of the receivers and having a wireless connection on the device. But the device sort of like degrades over time in terms of how well it's able to send. So this is in terms of its clock. So that degrades well over time, but within the average deployment time that we see, which is usually 8 to 10 years, it's usually a bit rock solid. So we do factor in that we get the best clocks that go on the devices in order to ensure that it's spot on over time.
Okay. Okay. Yeah. Any other questions? I saw we have some new people coming in. So Tariq, any question?
I was just wondering about something. You were talking about, obviously we're talking about inputs and outputs when it comes to sending information up to cloud and then getting it back from the cloud in a certain amount of time, and then perhaps connecting it to some sort of actuator to action to change a state in a process. So I was just wondering, is that a very reliable way to switch on and off an actuator compared to normal industrial control systems?
Yes. So with regards to, it depends on the use case. It really depends. Within, for example, industrial use cases whereby you have, for example, like programmable logic controllers, you'd find, so the question is power readily available? If power is readily available, probably PLC or any sort of like local control system directly on the plant is more reliable at any time. But also you have cases whereby you do not have a lot of power on the devices and there is no source of power available. Therefore, this sort of model excels within that use case whereby there is minimal power, and thus you need to have, the communication medium has to be wireless, and plus there's no power. So that's where this sort of like topology or arrangement excels at.
Okay, thank you.
Welcome. Okay, great. Is there any other questions?
Yeah, and I think if anybody else has a question, yeah, I think we can carry on.
Okay, great. So I will handle this. I will give this to my colleague, Adams Okode, to handle the software section. Adams, please take over.
Okay, just a moment as I share my screen. Okay, so thank you, Alois. Thank you for sharing that incredible presentation. So as we move on, so we work in teams in IoT. So you have the hardware perspective of things, you have the software perspective of things. So just to like handle that data flow, I'll come in and just explain a bit of how within Coyote and from what I've seen within my experience, how we handle data within that space. So what I'll talk about within my presentation will be APIs and data transfer. That's just the common protocols that we use, the common data types that are transferred over the APIs that we also use within our day-to-day work. Data encoding and decoding schemes. So you'll find that most of the distributors or probably manufacturers within the IoT space have their own encoding schemes for how they transfer data over the low power wide area networks and also over the high power wide area networks. And I'll just talk a bit about that and how to handle that if probably it comes up within your day-to-day work activities. Data storage and visualization. So this is now making sense of whatever data you've collected from all these devices, because IoT generates a lot of data over time. So just to move on just a bit about the APIs. So this is just sort of like introductory stuff, but quite basic within the software development space. Most of our APIs, internal APIs, and I'm sure most APIs within the world, a high percentage of APIs within the world use REST and RESTful sort of scheme, transferring JSON data on top of that. So JSON, essentially, just to give a brief, but there's a link that I think you'll find more information on for the RFC. JSON is sort of like a key value pair data sharing scheme, and it's usually sent over HTTP in form of string, can also be sent over MQTT protocols, still in string format. Graphical APIs are sort of like a new trend within the sort of RESTful API scheme, and this allows you to like select the particular parameters that you have, because you'll find that most APIs online, like if you take an example of the LoRa server, the LoRa kind of data output, or even if you're familiar with the Sickfox network. So Sickfox is a company in also France that has come up with a low power data network, and we use it a lot of within a lot of our projects. So just so you will find that the data dump that they push to us over the webhooks that we provide to them is usually large, but with graphical, which is graph query language, it allows you to select the specific parameters that you want and leave aside all the other overhead data that comes with that, which increases speed, just to mention that. You have protocol buffers implementation. So protobufs are commonly used within the gRPC sort of protocol. So gRPC is also a communication, sort of like I'm sure you've heard of or know about remote procedure calls. So it's just like an implementation of that to allow us within our new age to like communicate over the APIs and send data. One advantage of this is that it sends quite minimal data. So by minimal data, I mean you'd have very minimal overhead, and this makes your communication faster. You'll find that most enterprise applications implement this to actually within in-app communication of the various services. So this is taking the microservice architecture into account. You find that this actually increases communication between the services quite much. We'll also talk a bit about XML implementation. So this is quite a legacy sort of way of implementing the APIs, but you find that most organizations or enterprises still use this kind of communication to transfer data. So within the IoT space, I haven't encountered any API that still uses XML to transfer data, but it's something to like just look into and just have like a glimpse of how it operates. So this is just like a brief of all the data types that I've talked about, the common data types for APIs within the IoT space. So you have the key value pair JSON string, you have the XML node. I just put there, having all the data types within it. You have the protocol buffer, which defines the data types, and this also allows you to communicate within that space. So that's just like a brief introduction of how our APIs communicate and how generally most APIs communicate. So we'll move on to data encoding and decoding, and I've taken Sickfox into account while doing this. So I mentioned that we've worked on a lot of projects implemented on LoRaWAN and also Sickfox. So Sickfox is sort of like a paid LoRaWAN, and they allow you to integrate your device to their network. That's if you're a device manufacturer. So they have extensive documentation online. You can go and find the specifics on how to do an integration for your device to the Sickfox network. They have wide coverage within, I'm not sure if they have enough coverage within Mauritius, but I know within Kenya, they have about 80%, 70 to 80% of the population. They've covered 70 to 80% of the population. And how probably it helps if you compare it to the LoRaWAN network is that you do away with the cost of actually doing the network implementation, and you just directly dive into device manufacturing and software integrations. So usually, as I mentioned before, usually they just send a dump of a JSON payload, a huge JSON payload to your side with a lot of overhead information. But the key like data byte that you want is usually within the data payload that they send, which is usually a 12-byte data payload that they send to your side. And it's a standard that data payload will be 12 bytes, but you find that different manufacturers have different schemes of how they encode all their device data into that 12 bytes. So I'm sure within your day-to-day work, you've also sort of encountered where you have like a limited kind of space, and you have to sort of like encode your information and try to put everything that's important into that. So the image is not quite clear, but I think you can get a grasp of sort of like what exactly goes into that 12 bytes. So this is a sample actually provided on the Sickfox website. So this is what like we do on a day-to-day basis. So the payload is 12 byte string, 12 byte hexadecimal string, and you find that the first five bits have carry the battery level information, and then the next probably 2 bits carry the reserved, it's reserved for something probably, and you have, so that's like the scheme of how this actually works. You find, so I'll just mention probably, there's a manufacturer that we work with called Zena. They have smart meters. They are called Zena AMR meters. So they have a similar documentation. You find that you have to integrate to them. They have a different encoding from probably another manufacturer who has a different kind of meter, still communicating on the same network. So you find that probably there has to be some sort of way to standardize this. I'm not sure anyway, probably if anyone has a suggestion or has heard of something of the sort and probably has come into such a problem, probably can mention, because within our internal operations, we find it sometimes cumbersome to integrate to all this, being that there is no particular standard of how these devices communicate. You find that you have to constantly keep doing different integrations for different devices. So essentially that's what essentially is within the data encoding and decoding. So just manufacturers having their own scheme of encoding data, and us doing the implementation to decode the data for the different devices. This is mostly common in low power networks, but in high power networks, since you have like the bandwidth to transfer whichever data you need, this is not quite the problem. You can have JSON dumps for any sort of data that you need, and it's a bit easier to integrate to a high power network, just within the decoding and coding sort of sense. So I don't know if you have questions on that before we move on.
So I just have, I think, one question, if nobody else has any question about this. So we have, like Mauritius is 97% covered by Sickfox. And recently there was a talk organized by the Sickfox partner in Mauritius, and one of the things that's striking is that it's low cost, well, not low cost and low energy. For Mauritius, it costs us about €1 per month per device to connect to the Sickfox network, and you're only allowed 110 messages upload per day. So do you find that this is sufficient, because if you're tracking, for example, cargo, that's probably okay. But let's say if you have a Sickfox implementation that's something more critical, then don't you feel that, that the 110 messages are a limitation?
Yeah, so that's actually a concern. So we work closely with Liquid Telecom, who are like the Sickfox providers in Kenya. So you find that we actually raised that issue to them, and they mentioned that for clients or for people who want like a higher frequency of a higher data rate, you can talk to them and actually get a customized option. So probably you would not be communicating on Sickfox. That's what they mentioned. They'd give you like a dedicated link for your devices to communicate on. So because they find that most of this, a common example is car GPS trackers, which push real-time information to the dashboard or to the BI analytics thing. You find that the data pushed sometimes is larger than even the 12 bytes that they provide for on Sickfox, and they have to like provide a sort of like a dedicated link. It would have low bandwidth because you're just sending out data and not huge data frames like images or videos, but yeah.
Yes.
I could also add just a bit onto that.
Okay.
So within the sort of like Sickfox ecosystem is that they do know that there is this issue that everybody talks about, but it's also because like they're using the free band. That means that network operators don't pay any license cost as opposed to what the cellular operators do. But one thing that Sickfox is used in, especially, is when you talk about jamming resiliency. Especially when you talk about things like car tracking. Usually you'd find that vehicle tracking, they would send over cellular, but then they would use Sickfox as a backlink because when people do steal cars, for example, in South Africa or even in Kenya, is that they put GPRS jammers right on the car. So that means that your tracker or your immobilizer is unable to be commanded directly from the cloud. But because Sickfox is resilient, that's one use case by which they're looking at. So they're specific niches.
Okay, I'll just show you, like I get my boards from a company called PyCom, right? So this is like my PyCom board. I don't know if you can. So this is my PyCom board. And in this board, you can have Sickfox, you can have LoRa, you can have Wi-Fi, and you can have Bluetooth. So this is the antenna, Sickfox antenna. And this is the antenna for LoRa. And this is one of the solutions that we came out, again, for our air quality, the air quality project I was working on, is that because we had like multiple networks available on these boards, depending on which one is available. So for example, same as you were talking about, like keeping the Sickfox for when all other networks are not working. And this just with one board we got connectivity to 4 different type of network. And we were also using Sickfox to track, because we wanted to place the air quality sensors on vehicles and determine how like traffic jams is related to air quality going down. So this is why we needed to have regular updates being captured by vehicles. Yeah. Okay. Any other questions from the class? Okay.
Maybe
Yeah, Emmanuel. Yes.
I could ask if you get any issues with data corruption, like if packet is sent halfway or it's encoded wrongly, and how do you normally deal with it?
Okay, so just thank you for that. So just to answer that, so most of the devices that we deal with, yes, sometimes data comes in corrupted, or sometimes there's a blip in the network and the data comes in half. So what we do is most of our devices usually send twice or thrice within the time frame that they've been allowed. And this allows for like sort of like a redundant sort of scheme, so that you have at least two readings. So I'll just give an example of the water meters that I was talking about by Zena, the Zena AMR meter. So it usually sends at least twice a day. So even if one of the values is corrupted, you at least have the other to compare to. But also, it also depends on your business model and how you want to view the final data when you're doing like analysis. So as much as you have it sending twice a day, both of them might be corrupted, or you might not even receive the readings for that particular day. So you have to at least build it within your application, if that's what you're coming up with, so that when you're doing analysis, you cater for probably that one day that you had no reading, or probably the link got broken and you had like a half packet being sent to your site.
I could also add something small also, because I think this is a problem that is solved on both the hardware and the software, is that directly within the network and the hardware is that we essentially have certain data bits that we add onto the message called error correcting bits or messages. And what it does is that it's sort of like, it's a mathematical algorithm that goes through each of the messages, calculates something, a unique number, places it on the message itself, of which once it's received on the server does the same reverse operation, go through the payload itself and calculates this sort of like unique value and compare. Usually you find these are called either cyclic redundancy checks. There are various forms that are used, more advanced. But yes, this is just also one of the ways by which we also check for data corruption. And they're not foolproof. You might find that, for example, 8% of your data based on the mathematical algorithm, 8% might show up as correct, but yet it's not correct. But it's very rare for us to find this. You usually find that, yes, it would say yes, it is okay, but it's wrong. But we find that the data payload that is sent does not match up to whatever we had received previously.
Okay. Yeah. Thank you, Alois. I guess, did that help out?
Yeah, that explains it. Thank you.
Okay. No, thank you. Any other questions? Yeah. Okay. Thank you. Then I think we can go on. So the next bit is on the infrastructure, so the architecture bit. And for that, we look a bit into the open source software that has been published out there that actually helps you to come up with sort of an IoT infrastructure, just straight out of the box. So on the screen, we have a few mentioned there. So I'll just give a brief of each of them, and then we can go and look into the actual architecture. I'll use main flux as sort of like a sample for this section. So you have the first one, which is LoRa server. They changed their name to, I think, Chap Smart or something. But if you just type in loraserver.io on your browser, you're able to get their documentation. So LoRa server is directly implemented to support LoRaWAN and the LoRa protocol, and it's quite extensive. You have the gateway software, you have the network service, you have the application service, you have a documentation on the protocols that they use. They have a bit of MQTT. They have gRPC within the LoRa server. They've explained extensively how it works. Similarly for main flux, so main flux goes a step further because it does not strictly stick to the LoRaWAN protocol, but goes further and implements COAP, that's Constrained Application Protocol. It has MQTT, REST for your REST callbacks. Yeah, so those are the main sort of like protocols that are supported by most of this. So things both the same, Thinger the same, and also the Things Network, which is sort of like an open source LoRa server, pre-hosted LoRa server. Yeah, so you find that if you want to like start up like probably a development site, say you want to test out, you have like a new sensor in the market and you want to test it out, probably see its capabilities. So it's advisable to use one of these to just like test out the operationability of that particular sensor. And we also use this in production. So you'll find that Mainflux, Thingsboard, Thinger, also Things Network. They have Things Network specifically, since it's not self-hosted. They have like a paid version for much scalable scheme of it. You have Mainflux, Thingsboard, and Thinger, which are self-hosted, sort of like containerized. And if you're familiar with containerization, so it's sort of like a new scheme within the microservice architecture kind of development, where you containerize your application so that when you're doing the deployment, you don't have to reconfigure your servers or your development environment. To once you just use probably a tool like Docker, which is common within that space. You just run the containers on top of your Docker machine, and within minutes you have like a fully operational architecture in play. They're also contain sort of orchestrated by Kubernetes. I know Mainflux does that, so it's scalable for actually production. And I'd say that we've been alluding to move towards this, because we find that most of the time when you're integrating probably a new service, by a new service I mean a new sensor within your system, you have to develop for that particular, if probably it's communicating on MQTT and your service is tightly coupled to probably HTTP, then you have to have an MQTT broker that brings in the data. So you find that this already have that implemented. So what you just have is to have it sort of abstracting your main backend application, and you can, so Mainflux, both Mainflux, Thingsboard, and Thinger, also the other two, which are Things Network and LoRa Server, have a means of pushing the data to your side. So you can put in rules, and callback methods, sort of like webhooks, to push the data in JSON format if you wish, or you can even use within Mainflux, Thingsboard, and Thinger, they allow you to use other protocols. So that's MQTT. You can use gRPC, also COAP, to push the data to your end application. So I think they're quite useful. You can have a look at them and see if they can help you get started. Okay, so what we have here is sort of like just a sample architecture for. I picked Mainflux because it like speaks to most of the others, so they're implemented in more or less the same way. So what we have here, it's like sort of like a container. I would call it a container for one node of main flux running on probably a development site. So just to get into it, so what we have, probably I'll talk about the bits within the image, and also you can go through the text as I go through it. So you have the first layer, which is the CLI, the UI, the app, and the device. So the app speaks to your end application on your side, whatever you want to integrate to the main flux ecosystem. The CLI and the UI, main flux comes out of the box with a CLI and a UI, which allows you to visualize the data that's been collected from your devices. With the CLI, you're able to go through the command line, issue some commands to your CLI, and get outputs from the main flux ecosystem. The app, as I've said, it's your end application, so it can be directly integrated to the main flux ecosystem. The device, this speaks to the end device, the sensor that you integrated with whichever protocol that is supported there. So for this, you have the HTTP protocol, MQTT, WebSocket, and COAP. Good. So we'll skip the main flux UIs because this is just like an extension of the top four nodes. Top four avenues that have been explained. So the next layer is the HTTP sender, the MQTT WebSocket sender, and also the COAP protocol. So also within main flux itself, it uses these protocols to communicate to NATS. So what an NATS is, or just call it NATS, is sort of like a message broker. So if you're not familiar with message brokers, so I like to call them sort of like a caching system for your application. So what message brokers help us with is, so initially you'd queue, like when I started development, I used to queue using my DB, but you find that you have your application increasingly becomes slow because of the writes and reads, because you're actually pushing data to your actual storage. But what message brokers do is they help within that process and make it a bit faster. So you have in NATS, you have Apache Kafka, you have Redis for that. You also have RabbitMQ, which has been used for a while. You can use either of that, but for the main flux architecture, they chose to use NATS, which is actually good. I think from their survey, they say that it's the fastest. Anyway, so just to explain that, so from that layer, from the messaging bridge, that is the HTTP, MQTT, and WebSocket protocol, the COAP, the data is pushed to that message broker, which then sends out the data to the writer, which pushes the data to your DB. So Cassandra in this case is the database. So you notice that Cassandra is picked because of its schemaless architecture sort of property, because within IoT you find that most of the data that you receive is usually not unstructured, but you may be collecting data from different devices, which, as I mentioned before, send out data differently. You just, instead of reconverting that data to a standard format and storing within that space for starters, you can just push it to a schemaless DB, then put in a service that will later run through the DB and sort of like clean that data, just to speed up your processes. Yeah, so just to explain what happens at that NAT. So if you're also familiar with message brokers, you'll notice that there's usually two key terms, which is the producer and the consumer. So the HTTP sender, MQTT, the messaging bridge, just in short, it will act as sort of like a producer for data. So you produce the data into the message broker, and then you have services running, checking if there's data, and then the consumers on the other end, that's the consumers on the other end, pick the data and then push it to your persistent storage, which is Cassandra in this case. So, and how main flux now, how the top layer UI accesses that data is via the reader and the manager. So the manager writes the data, accesses the data, writes, edits the data, and you have the reader that provides, pushes the data back to your interface for whichever operation you'd like to use it for. So essentially, that's how most I find most IoT architecture sort of systems are designed. You'll find for ThingsBoard, it's sort of similar. They just used a bit different technologies. Probably they use Redis instead of NATs, but yeah, essentially that's how you'd get started with coming up with an IoT architecture. So yeah. Yeah, I don't have anything else to say to that. I don't know if you have questions on that. You can just shoot them up.
Any questions from the class? Victor, maybe? Or Stella?
Yeah, so is this like so do we see a change in this IoT framework based on probably this solution if you have a different kind of solution? Do you need to change?
Do you mean to say like changing the architecture to match whatever you're trying to solve?
Exactly.
Yes, so just to answer that, so yes, you can change it. So MainFlux is open source. So if you'd want to change it, it's possible to do that. But how I see it mostly implemented, or from what I've read up online and also from what we do internally, is we have it abstract our main application from our side. So we sit behind the MainFlux sort of architecture. Once we get the data, we store it within the persistent storage for this particular MainFlux ecosystem. And then later we have services that push it to our end application. So you can keep your architecture as is, but just have it sort of like outside that, pushing data inwards. But it's also possible to customize it to fit your business needs, because it's an open source sort of it's an open source thing, and that's why it's commonly used. All the software that I mentioned there are open source, apart from the Things Network, which is not self-hosted. Yeah.
Okay. Thank you, Victor. I hope this answers the question that you had. So I have one more thing. So the more and more you find that MQTT is, like whenever you're reading a tutorial about IoT, whenever you're reading some implementation or case studies, more and more MQTT is being named more often. Like is MQTT becoming like the standard for this, or do you see that there might be other bridge software that could be used, or message bridge software that could be used?
So I actually agree with you. So most of the IoT implementations, even within Kenya, are mostly running on MQTT. You have to find some sort of MQTT integration for that particular service if it's launched publicly. I also find that COAP is actually coming up. It's a bit younger than MQTT, but also offers a bit, because I find that MQTT you have to define, because you realize within, most people are used to HTTP, and you find with HTTP the REST protocol, you have get, post, put, verbs. For MQTT, you have to find a scheme of how you will implement that into your sort of development and into your architecture. But COAP comes with that out of the box. So it's also coming up, but I find that MQTT is definitely the way to go in the recent years within IoT. Yeah.
Okay, thank you. Thank you for that. Any other questions? Because I know you have our students currently in the D4I modules have started looking at LoRa, IIoT, and MQTT. type of services. So do you have any questions, Klaus? Okay, seems like no more questions. I had another question. So, okay, back to this MQTT thing, because if you look at, you know, like service providers, for example, Azure uses a lot of MQTT, and they have their how it's called, IoT hub type of implementation. Is this reflective in what something like my MainFlux would also provide?
Yeah, so actually, yes. So it's similar. The Azure backend actually provides something similar to what MainFlux provide. The only difference would be that MainFlux can be self-hosted. They have a cloud version, but you can pick it and actually host it yourself. An extra thing that MainFlux offer is that for the Azure sort of dashboard, you have you'd configure rules and then send the data over to your site via HTTP. MainFlux allow you to also configure between your application, your end, because however it comes to have, you have to like push it to a custom dashboard to actually make sense of that data. So the connection between that and dashboard and MainFlux can also be MQTT. And MQTT has been known for its speed, and I think that's good.
I have one more question on security.
Yeah.
So do you find like, because I think now, you know, more and more customers are becoming more aware of security requirements.
Yeah.
So how do you handle like security of your devices, that nobody goes and tampers with the device, or security when you're scanning your data?
Okay. So I'll talk about the software aspect of it, because security comes in both aspects, hardware and software. I'll talk about the software aspect. I'll let Alois talk about the hardware. So you find that most of the manufacturers who come up with like this IoT devices, I'll take an example of Camstrap, who are a meter manufacturer who we've worked with. They have keys for all these devices. And to actually decrypt, because they use Sickfox as their medium of communication, because it's like widely spread. You find so to actually decode the data on your side, you have to have the particular key for that for that device. So that sort of encryption is very, very adamant in keeping the security of your data. And also, just so from an application perspective, we heavily utilize tokenization of data to actually receive and get data from all of these protocols. You need a token to actually access each of these services and get data from them. This also helps in knowing where the actual request came from, and also knowing just data auditing in few accounts. Yeah. So that's from the software perspective of things. Yeah.
I could also add onto the same topic with regards to security. Yeah, security is a very key issue, especially, but one thing when we are going into a project to do it with regards to security is that we scope the security threat in terms of what is at risk. That way we do not over-engineer and we do not under-engineer. So once we do the security modeling as to seeing what is at risk, is that now we start the whole process of organizing the devices. Usually what we do is that, as Adams has mentioned, is that we have a unique key per device, and one needs the keys. So you'd have either on the devices, for simple devices that do not have power or that have power limitations, is that you'd have a type of encryption known as symmetric encryption. So that includes encryption such as the Advanced Encryption Standard, AES. So that is usually used on power limited devices. On industrial devices whereby you do have power, you are allowed to go on to other forms of security implementations, such as public encryption schemes, whereby you'd have a decryption key and an encryption key, of which you can share out the decryption. How does it go? Yeah, so you share out one of the keys with regards to identification. So there's a public key, or sorry, it's not encryption, decryption. It's public key, private key. So you share out the public key that identifies the device. Any system can authenticate the device. But for the private key is only stored on the device. And if you do need to have a copy of it, it's usually advisable not to have it on the cloud, but rather to have it on some form of cold storage, something that is isolated, sort of similar to a military use case. You'd have it sort of like on a flash disk outside, stored in a vault, or stored somewhere that is outside any network. I think you're on mute.
Yeah, sorry. Thank you for that. And thank you for talking about security, because I think security is something that is not typically done by design, and it's like comes as an afterthought. And I think it's good to talk about security context in IoT. Any other questions from class? Okay. Thank you very much. I think we are 1 minute from our first break of the day. Right, Persis? Yeah, I think. Okay. So thank you very much, and thank you, Adams and Eloise, to come and give us this interesting talk about IoT. Our students are, like I said before, they're currently doing the D4I module, where they're looking at IoT systems and implementation in industry. And they're supposed to be building the digital twins for the capstone project that we have. So thank you for talking about IoT and IoT industry to them today. Right?
Thank you for having us.
Thank you.
Oh, you're always welcome. So Persis, we're going to break, right?
Yes, we're going to take a break. Thanks, Adams. Thanks, Eloise. We'll take a break and reconvene at 11 a.m. CET.
Okay, thank you.
Adams and Eloise will be in touch, I guess, on email as the class continues.
Thank you, Persis. Have a good day.
Thank you.
Okay, thank you. Thank you very much. Okay, guys. So head out to your break, and then see you in 30 minutes. Right? Okay.